Hello. In this video, we are going to derive a relationship between the expansion coefficient alpha and the isothermal compressibility K sub T. Your mission, should you choose to accept it, is to show that the partial derivative of P with respect to T at constant volume is equal to alpha divided by K sub T. When we write show, it means exactly the same thing as prove. So I like to alternate the words because they mean exactly the same thing. Both show and prove mean prove. Recall that the expansion coefficient alpha is defined as 1 over the volume times the partial derivative of V with respect to T at constant pressure. And a useful relationship we can get from this immediately that will be useful later on is to simply multiply each side by the volume. And it gives us that alpha times the volume is equal to this particular partial derivative, the partial of the volume with respect to temperature at constant pressure. The isothermal compressibility K sub T was defined as minus 1 over the volume times the change in the volume as a function of pressure under a constant temperature condition. And again, we can make the same kind of transformation here that will be useful later on by multiplying each side by minus the volume in this case. And we get that minus K sub T times the volume is equal to the partial derivative of the volume with respect to pressure at constant temperature. The volume of a system can be thought of as a function of the two variables, the pressure and the temperature. Importantly, the volume is a state function, just like the internal energy and the enthalpy. So that means that we can write an expression for the exact differential of the volume in terms of the pressure and the temperature. Now we know that the form of the coefficients of dP and dt have to be of a particular form. We have the partial derivative of the state function with respect to that particular variable. So v with respect to p here, and then we have to have the partial derivative of v with respect to the temperature as a coefficient here. And since the pressure is changing, we have constant temperature. And for this particular partial derivative, we keep the pressure constant. Next, we want to divide each side by dt. And next, we are going to impose a condition of constant volume. If we impose constant volume, we get partial of V with respect to T, constant volume circumstance. We have change in V, the pressure at constant temperature. This converts into a partial derivative of P with respect to T. And recall, it's a constant volume condition. Plus dt just becomes 1. So we're left with the change in the volume, the function of the temperature, under a constant pressure circumstance. This is a very interesting partial derivative. Notice that the change in the volume with respect to the temperature under a constant volume circumstance. So the idea that the volume is constant tells us this partial derivative has to be exactly 0. If you have a constant, then the change is equal to 0. So this is 0. And the rest of the expression we can write down as an intermediate step. Let's now subtract the partial derivative of V with respect to T at constant pressure from each side. And that gives us the left-hand side, the change in the volume with respect to pressure under a constant temperature condition, times the partial P T V is equal to minus the partial derivative of the volume with respect to the temperature under a constant pressure circumstance. Notice on the right-hand side that this expression, the change in V with respect to T at constant pressure, we had already derived a result for that, and that was equal to alpha times V, where alpha was the expansion coefficient. And that gives us that the partial of V with respect to P under constant temperature times the partial of P with respect to T under constant volume circumstance is equal to minus times alpha, the expansion coefficient, times V, the volume. So we're part of the way to our final result. We have incorporated alpha, and that suggests that our next step will be to find some expression that is equal to KT in our current expression. Recall that we had previously derived an expression for this particular partial derivative, and we found that it was equal to minus KT times V. So let's make that substitution here. Minus the isothermal compressibility times the volume. And we still have what we had before, which was the partial derivative of P with respect to the temperature under a constant volume circumstance. And that is equal to minus alpha, the expansion coefficient, times V, the volume. And we only have one step left to go. We can divide each side by minus K sub T times V. And we get, as a result, that the partial derivative of P with respect to T under a constant volume circumstance is equal to alpha divided by KT. And this was exactly what we had wanted to prove. Thank you very much for your attention. Have a good one.